Hello, my name is Haley Rhea, and this is my term project for control systems over permanent magnet DC motors. Inside the motor, there are permanent magnets that supply the field flux such that external current is rendered unnecessary. The motor also has a wound armature and a mechanical brush inside of it, similar to other motors. Permanent magnets can be made from a number of different materials, including ceramic ferrites, rare earth metals, and alnico. In permanent magnet motors, a wire serves as an electromagnet when electricity passes through it. The electromagnetic coil is attracted to the permanent magnet, and this causes the motor to rotate. When the power source has been removed, the wire loses its magnetic qualities and the motor will stop rotating. In this way, a permanent magnet motor can be managed by controlling when and for how long the electricity is allowed to flow through the wire, and this determines how long the motor rotates. When choosing a DC motor for your application, it is important to weigh the advantages and disadvantages. Some of the advantages for using a PM-DC motor include the fact that they are easy to use and that they are simple in construction. This means that there's no winding required, as the motor does this on its own with the magnets. These are also smaller, and therefore they are good for putting in smaller machines. Some of the disadvantages, however, include the fact that the speed control is not possible because either the magnets are engaged or they aren't. It's also impossible to change the armature because the magnets are in fact permanent. Because of their relatively small size and low cost, PM-DC motors are very commonly found. Some of their uses are in automotive industry, such as the motors that are found in windshield wipers, in toys like RC cars and small robots, computer drives like disk drives, and small appliances like portable vacuum cleaners, food mixers, hand drills, electric toothbrushes, and several more. In beginning to model a PM-DC motor, some assumptions must first be made. Some of these include the fact that there will only be a single input and output. The input is a voltage source and the output is an angular velocity. Additionally, these PM-DC motors have a rigid shaft and motor and very viscous friction. For the purpose of this project, the specifications of this motor were chosen arbitrarily by me. I chose a rotor inertia J of 0.01 pound-inches per second squared, a viscous damping coefficient B of 0.25 pound-inches seconds per radian, a back EMF constant K equal to 0.02 revolutions per minute, an armature resistance R of 0.96 ohms, and an armature inductance L of 0.5 Henry. The PM-DC motor block diagram can be simplified as omega over V, which equals K over the quantity of R plus LS n quantity times quantity JS plus B n quantity plus K squared. After the initial MATLAB calculations, a settling time of 1.91 seconds is found, and the final value is 0.0768. This can be made better by further response criteria, and therefore we will attempt to make it better. The further response goals that I have set are to have a settling time of less than 0.2 seconds, a rise time of less than half a second, a percent overshoot of less than 10%, and a final value of 1. After implementing my response criteria into MATLAB, here is shown the final response. In the final step response, I am left with a settling time of 0.0159, which does meet our goal of having a settling time of less than 0.2, as well as a final value of 1, which is exactly what we wanted. Here is shown a model of our system, with the controller now included. The controller is the red box with the C in it. As we've seen, the SISO tool is a very effective tool that we can use in modeling these motors, and it can save a lot of time. It is also a good idea to add a controller to these systems, but it can't do everything. It is good at maneuvering, but isn't an end-all be-all when it comes to coming up with an efficient motor. If your motor is really bad, the controller can only do so much.